Well, thank you for coming. We are honored to have the chance to introduce you to Akka-http. I'm Mathias and this is Johannes, and we're the team behind Spray, which some of you might have worked with already. Who has worked with Spray so far? So who has written already some Spray that is in production? I'm sure. Okay, quite a few people, that's great. Well then some of this might seem familiar, but there are also quite a few things that have changed over Spray, so even for you guys this is going to be hopefully interesting. We're going to split the talk in two a bit, just so that we have both a chance to present what we've been working on for the last months. So, let's dive in. When last year it was announced that TypeSafe has acquired Spray, we got lots of positive reactions, but also a few questions, like this one, right? What's with HTTP and Akka? How does this really fit together? Why does Akka need an HTTP module? Isn't that somehow feature creep? Isn't this just adding too much stuff to an otherwise pure and clean framework like Akka? Isn't HTTP somewhat too high level, and how does it somehow connect to the actor hub, right? If Akka is about actors, why is HTTP in this? And it's a very good question, and it makes sense to look at the motivation behind this to understand why Akka-http does make sense, very much sense. So if we step back and look at Akka, who does not know Akka? All right, so most of you know what Akka is. And if you look at the website, Akka.io, it tells you that Akka is a toolkit and runtime for building highly concurrent, distributed, and fault-tolerant, event-driven applications on the JVM. So that's quite a mouthful. There's a lot to digest in there, but it does capture it. The promise is a bit more catchy. And it says, Akka wants to make it easy to build powerful and concurrent distributed applications, right? And there are two important things in here, right? There's concurrent and distributed, and concurrent is traditionally hard, as most of you have known probably by working with threads or trying to somehow coordinate and make sense of all the work that you want to do on a highly parallel machine that we have nowadays. And distribution, as we've seen in Roland's keynote this morning, is even harder. There are even more things coming into play and making it difficult for us. And Akka wants to make it easy. Now, if we look at what distribution means, then distribution ultimately means integrating. It means integrating the different parts that you have distributed, right? There's no distribution if you don't have a chance to integrate what you're working with. And between your own subsystems, this is somewhat easier because you control everything that needs to be integrated. And then if you look at Akka gives you something to make this easy. And currently we have Akka remoting, and there's Akka cluster, which is getting more and more features and making it easier and easier to work with distributed machines that you control. But there's also integration with other systems, right? Because the applications that you're building right now, they're very unlikely to live on an island. They're probably connected to the world, to all kinds of other services that you might be consuming or might be providing to the external world. And you don't control the clients that talk to your server, or you don't control necessarily the servers that you need to interact with from the client side. And this is where Akka-http comes into play, right? Because HTTP is the most successful integration protocol to date. Without HTTP, we wouldn't have the web and lots of other things. So HTTP is important. It might not be perfect, but it is the most successful integration protocol. And in order to enable integration with other systems so that you can build large distributed applications, also with systems that you don't control, Akka-http is crucial for it. So that's why it makes sense to have something that's performant and properly architected right in Akka to enable integration with other systems. So as most of you know, the origins of Akka-http are Spray, So Spray contains a lot of logic that you can already use right now to build highly performant HTTP server and client-side things. And if we look closer at what Spray is, it's an embeddable HTTP stack. So it's not a container that you deploy your application in, rather it's a library that you just depend on, and it gives you tools to consume and provide HTTP-based services. And the focus is more on integration layers rather than web applications. In the beginning, it might not be so clear when would you use what, when would you use Play, the obvious candidate if you want to build a web application. But since we're coming from this distribution idea, the idea is integrating systems, right? So you can use Spray to build a web application if you really want to, but there are probably things that if you want to build a modern web application, things like asset management and JavaScript support and Ajax support, all those things that are more front-end related, that you won't find any support for in Spray. That's where the difference comes from. And also it's server and client side, right? So if you look at Play, then there's no client side because it's a server-centric web application framework. And the benefits of Spray are that it's fully integrated into the type-safe stack, so it's completely written in Scala. We use the same configuration tools, the same debugging tools, the same configuration systems as you do for all the rest of the application. So it's a seamless integration also within your application stack. We look quickly at the features, then Spray gives you an immutable case class-based HTTP model. So there is, for everything that you work with in HTTP, there's already a case class or an object or something defined for you that you can just work with. The focus is on being fast and lightweight, so nothing heavy, not too many features in one place where you don't need them. And then we have higher level components, especially on the server side, that enable you to write concise and yet very flexible code to define what your API definition looks like. And we'll see later on in the talk what this is going to be like in Akka-http. And of course, since we're based on Akka, we're fully asynchronous, non-blocking, actor-friendly, modular, testable, all those nice buzzwords and adjectives you can find there. And it's Scala and actors all the way through, so we're not wrapping, Spray does not wrap any Java code, like many others that depend on Netty, for example, which is an excellent base, but it's not written in Scala, so it has its own configuration, its own debugging, its own thread pool management, and so on. So it doesn't fit in as nicely as a pure Scala implementation. Now, even though Spray is great, and lots of people already use it in production for a long time, there are also some weaknesses that Spray has. Now, we've been aware of them for also quite a long time, but they're not that easy to fix if you have already a large base of users that depend on some kind of continuity, and also because there were a few abstractions missing for us that made certain things hard. For example, the handling of chunk requests. HTTP has a feature where you can send a response or a request not in one go, but in small chunks. And that's sometimes not as easy to work with as it could be. Also dealing with large messages, if you have, we'll see that later, if you have a message that is several gigabytes and you want to handle it efficiently, it can be tricky in Spray. The reason being that we didn't have at the time a proper abstraction to work with this, right? Because the key idea is always non-blocking asynchronous, which demands different kinds of APIs than what we've been using traditionally in the Java world. And then the high-level structures, the DSL, which is quite powerful, also comes with a few traps of its own that sometimes users that come into Spray newly, they kind of tend to fall over certain things which we can improve, and we are improving now. And of course, missing features is always something that you can write in any chart, and we'll always have missing features. The hope is that in Akka-http we'll have less missing features, or fewer. So let's take a look at one particularly interesting weakness of Spray, which is a case that we have actually had several times in our work with clients that come to us and say, look, help us, we have a certain issue with our application, how can we fix it? And this is the setup. It's quite common. Basically, the idea is you have some kind of business service, and you discover, wow, cool, there's this whole new stack there, Scala plus Akka plus Spray, and we can just we can build all our new stuff on this new stack, and it's great. It runs nicely, stable, all cool, but we still have some old services that we don't want to migrate, or that are not worthwhile migrating, and we just keep them where they are on their old legacy system, be it a servlet container or be a completely different implementation, but it's still around, right? It's a legacy backend, and for certain requests, we just proxy to the legacy backend, right? So this is what it looks like. You have a client somewhere that connects over the internet to your new backend, for example, with a GET request, and we just proxy that with Spray, which is not that hard, over to the legacy backend, which sits on the same LAN, and then the legacy backend replies with a somewhat large response, say it's a large file, and then we need to proxy that back to the client who might be in New Zealand on a slow connection. Now you might see where the problem is, because if you ask the legacy backend for a large file, and the legacy backend just says, okay, cool, here's the file, and just streams 8 GB at you across the LAN, across a really fast network connection, and we're in the middle with Spray kind of transporting that over to the client in New Zealand was really slow. Now, what happens? You get squeezed right there, right? Because you're drinking from a large fire hose, and you need to somehow funnel it through a straw over there. So what we need is pushback. We need to somehow slow down this old legacy backend with delivering the response at the speed that we can actually take it. And in Spray, this is not as easy as it could be. Because we're just reading from the socket that reads from the response, right? And we transport that over to the client, we try to feed it to the client, but we can't send quickly enough. And so what do we do with this? Do we buffer it? Do we overflow onto the disk? It's tough. And in Spray, the way it works is you go in and you tell the network layer in the bottom, stop reading from the socket now, right? I'm busy, I'm getting overwhelmed over here, stop reading from the socket. But your command to stop reading might not actually make it through before you out of memory or out of your application, which is just brittle and doesn't really work nicely. The problem here is that we're missing an abstraction to help us work with large amounts of data in an asynchronous, non-blocking fashion without any risk of overflowing. Okay, having that in mind, let's take a step back. Akka-http is something like Spray 2.0, right? If we were to write Spray 2.0, it would look like Akka-http. So we across all the modules, all the parts, we apply some polishing, we address the weaknesses, not only the ones that I've just shown. Then we add Java APIs, because everything in Akka, as you might know, has a Java API. We simplify the module structure a bit, because we might have gone overboard a bit with it in Spray. And there's one core improvement, and that's that we're now based on something that's called reactive streams. And that's a brand new abstraction that was put together, or is currently being put together by engineers from Netflix and Twitter and TypeSafe and Red Hat and other big shot guys that really know what they're doing. And they're putting together this new reactive streams abstraction. Now, the reactive streams are a big topic. Who has heard of reactive streams so far? Most of you, right. It's a very interesting topic, but we don't really have time today to deep dive into it. It's its own talk, and there are lots of talks already online that you might click into if you want to find out more about reactive streams. But in a nutshell, it's an abstraction, a streaming abstraction, that allows you to read potentially infinite streams in an asynchronous fashion, and with one important feature, which is back pressure, right? So if I'm not reading from the stream, then I'm implicitly or explicitly pushing back into the stream. Do not send anymore. I cannot get overwhelmed if I'm on a reactive stream. The nice thing is, if you build a large system with reactive streams, then this back pressure will channel through all the application, through TCP, over onto another machine, and through that out to, and so on. So it's a long pipeline, and it's very powerful, and we'll see a lot of stream-based programming in the future. But since we now have this abstraction, we can solve a lot of problems that we had in Spray, that we had because we didn't have reactive streams at the time. So where do streams come into play in Akka-http? There are actually quite a few streams when you think about, even if you don't know the details, they don't really matter, but there's a streaming abstraction, for example, for all the requests on one HTTP connection. As you know, an HTTP connection is just a TCP connection that transports HTTP requests and responses. And one connection can actually have several requests. You can reuse that. And you can also, if you enable HTTP pipelining, you can send a whole number of requests in one go. So you can send 10 requests and then read 10 responses, which is called HTTP pipelining. So it makes sense to think of the requests coming across one connection on the incoming side as a stream of requests that I can decide to read, or I can decide to not read, and then they will just back up to the client. In the same way, the responses on one HTTP connection are a stream, right? I can stream them out to the client, and if the client doesn't read them quickly or slowly, then I'll get back pressure, right? I can't send them, and that needs to traverse across the whole application all the way to wherever the data come from. And then if you think about the bytes of one message, then they're also a stream, right? If I read a request which might have a large entity, a large content, and that could be a gigabyte, and I want to read those bytes as I am able to actually digest them. So these are the places where we have streams in Akka-http. Now, if you look at the interface level, and this is what you're going to program with Akka-http, there are two sides. There's the client side and the server side. Let's look at the server side first. The the yellow stuff that you see here is what you are writing. That's what you supply. And one single HTTP connection that we see here has a stream of requests going into the one direction, and the server responds with a stream of responses that go in the other direction, right? And on the server side, your user application provides the connection between this stream. It closes the pipeline. It takes requests and it translates them, it maps them into responses. And if you stay within the stream abstraction, then the pipeline will be sealed, and any back pressure that comes in from what we've just seen, for example, the client not reading responses quickly enough, will propagate through the application all the way out to the request stream. So that's pretty clear. And on the client side, you don't provide this mapping between requests and responses, but you get it, right? Akka-http gives you something that translates requests into responses. That's what an HTTP client is, right? You send in a request, you get out a response. How that happens is none of your concern. You don't care. It's just what the client does. So you write your own long stream that translates employees into some data and merges it, splits it, and whatever you can do with the stream. And then there's one component, which is the Akka-http client, which translates requests into responses. Cool. So what does it look like in code? Let's look at the server side first. So this is our current guess for the server side in Akka-http. Let's see what this looks like. So we have something that's called a connection handler, and a connection handler is just a name for a flow. A flow is something that's provided by Akka Stream, which is the reactive streams implementation from TypeSafe. That is part of Akka. So together with Akka-http, actually in lockstep, we're currently developing another module called Akka Stream, which gives you a DSL and an implementation for the reactive streams API. So it's just a model for properly working with reactive streams in Akka. So one key thing in there is a flow, and a flow is just a piece of pipeline. You can see it as a hose with two open ends, and you stuff in on the one side, you stuff in requests, and on the other side you get out responses. And what you do when you write a server, you call http.bind with an endpoint and some configuration data. The endpoint is just what you want to bind to, right? Localhost port 80, for example. And then you provide this piece of pipeline, right? Exactly the yellow thing on the right. That's what it is. That's what you provide from your application. Because that's what an HTTP server is. It translates requests into responses. And what you get out of this is a source. That's also another abstraction in reactive streams. It's the endpoint of a hose that you can decide to read off if you want to. And if you decide to actually open that source and read out something, so demand something, give me the next connection, then this will actually cause the server to accept the next client connection that it's trying to connect. Right? If you just read everything that comes in, if you just completely drain this source, then the server will simply accept all the connections that are currently waiting for acceptance as quickly as possible. If you don't read this very quickly, for example, if you only read it once per second, if you only demand out one item per second, then the server will only accept one connection per second. So that's how you can throttle the server, right? And if you cancel that, you can, in a reactive stream, you can also say, look, I'm just going to cancel my subscription to this data stream. I don't want to read anymore. I close it. Then closing this source effectively means unbinding, right? You're not interested in any new connections from the server anymore, which means that you can unbind. So that translates naturally into APIs are working with TCP, because on the TCP level this will look exactly the same in a streams fashion. Okay. Let's see what a simple HTTP server could look like. Here, this is the simplest, one of the very simple HTTP server that write with Akka-http using this API. So there's still this IO-HTTP thing that you might know if you've worked with Spray. It's an extension of Akka that gives you an entry point to the API. And then you just call bind localhost 8080, that's pretty clear. And the second parameter that you give it is this piece of pipeline that I just talked about, right? And this is one of the most simple ones. You just map, right? The piece of pipeline is a mapping stage. So it maps incoming things into outgoing things. In this case, in a one-to-one fashion. So there's a request coming in, and we pattern match on it. And there are two different cases, right? Either it's the first case or it's the second case. If it's the first case, which you might be able to read just like that, it's a GET request to a certain path. And we're not interested in all the other properties like the headers or the protocol version or the entity of the request. We just map that into a simple response. By default, it's going to be an OK, 200 OK response. And the catch-all just says, okay, it's a 404, unknown resource, that's it. That's all the server logic that I need to write. Now there's one thing at the end which is run with black hole sync, which looks funny. Basically, that's Akka stream speak, current Akka stream speak, for just draining the source into a black hole. You don't care about details of the accepted connections, and you also don't want to apply any throttling or any back pressure or anything. You just want to accept everything that comes in, which might be a problem in your real world. In your real world application, you probably don't want to do this because you might want to protect yourself against DDoS attacks or anything. So you might want to watch how many connections you actually accept at the same time, and you might say, I'm not going to be accepting more than 10,000 concurrent connections or more than whatever, right? You configure it. But this is what it looks like. And what the important thing here is you only specify the forward channel. So you only write down in this logic how you want to deal with data items that go through. There's no back pressure involved here, right? You don't need to concern yourself with the information that flows into the opposite direction that tells the source to slow down if you're not reading fast enough. Right? That's implicit, which is good because you don't want to deal with it. You just want everything to do the right thing, and most of the time this is possible. So this is great. This server will never blow up. It will just always run nicely as long as you stay within the Directive Streams API. So on the client side, it's similar, but just inversed, as we've seen on the picture before. So here you say http.connection client flow, that's what you request. You ask Akka-http to give you a piece of pipeline that you can put into your own streams. And you'll get back, if you want to connect to a certain remote address, you get back a piece of pipeline. This is HTTP client flow. And it also has a funky parameter called key in there, which is something that you specify. We don't really care. It's a helper thing that allows you to attach a certain context of your own choosing to a request that you will get back with a response belonging to that request eventually. Because sometimes this flow, if you move on to higher level APIs, might actually represent a connection pool to the server. right? So if you have 10 connections to a certain server, like some Google API, then the response for a later request might come in before a response for an earlier request. So they might come in out of order, which makes it hard for you to associate which response is for which request. And if you attach your custom context T, whatever it is, then it's much easier for you. This can also be a closure, for example, or some kind of whatever your application needs as a context. But here it's important to understand that Akka-http will give you a piece of pipeline. If you use the Streamify API, there will be other APIs as well if you don't want to work with streams, but this is the core. And in the bottom you see something that's interesting to understand as well. We can also, basically what the HTTP layer does is it's simply raising the level of abstraction from TCP to HTTP, right? And if you ask Akka-IO, which we'll see later, on one level down, on the TCP level, you'll get the same thing from its client-side API, just on a byte string level. So it's a piece of pipeline that converts byte strings to byte strings by sending them to the server and reading of the server. And then the HTTP layer simply upgrades a piece of pipeline to actually represent HTTP. So you can also just say, okay, I talked to the IO layer directly. Here's a piece of pipeline I got from them, which represents the TCP client, and I give it the HTTP layer, and the HTTP layer turns it into an HTTP client, right? That's the raising level of abstraction. This API would allow you to configure your TCP connection any way you want. For example, special encryption settings or anything, right? You can also use it for testing. You just give it a special transport. We don't care what the transport is. All we do is actually doing HTTP. So that's interesting. I think the next part is going to be Johannes's.
Yeah, right. So when we started writing an HTTP library, we were pretty sure the first thing we need is a proper basis, and that is a real model of all things HTTP really provides. HTTP is. So what we try to do is to write an idiomatic Scala model of all the things which are on HTTP. So basically it means that we have case classes for many of the entities, the request, the response, the headers, status codes, HTTP methods, modeled as case classes. So this differs a bit from what we know from Java, where we, like in the Servlet API, we have mutable classes to really set fields on the HTTP request. But in Spray and in Akka-http, we have a model which is mostly immutable. So, like case classes, most of the things can't be changed afterwards. So we didn't model only the basic things like requests and responses, but also most of the things which belong to headers, like media types, char sets, cache control directives, and everything which you would need if you really want to have deep control over how your HTTP is going to behave. Mostly we try to cover most of the HTTP stuff, but HTTP is really open in many regards. So like media types are added all the time. So yeah, you can add your own media types if you need it. So let's look at the most basic model we have in Akka-http, which is the HTTP request and the response. And you can see that we have fields for the things you expect to see in an HTTP message on the highest level. So if you think about how a request looks like, it starts with a method, then there comes the path to the URI, or the URI to request. Then we have a set of headers, and then usually in a request we don't have really a request body, but for example if you have a file upload you will have a request body, so this is the entity, and then we have the protocol, which usually is HTTP 1.1, but yeah, we also support HTTP 1.0 currently. So this is the HTTP response. It basically looks very similar because HTTP messages are responses and requests are very similar. So in response you have the status code, you have some headers, and you can see the HTTP header type is the same as in the request, and yeah, it's a super type of all the headers we have defined in Akka-http. Then again we have an entity. If you have seen it before, we have different kinds of entities. Here we have a response entity, which belongs to all body types which can occur in a response. And before we had a request entity, right here, which are entities which can occur in a request. And you will see later that there are some small differences which can occur in which position. Okay, so another important thing when working with HTTP is URLs or URIs, and so we try to split that up properly as well. So this is how a URI looks like in Akka-http. It has a scheme. Yeah. I mean, I think it's obvious. Okay, now, so as I said before, entities are really split up in different kinds of entities, and we introduced some kind of marker traits to denote which kind of entities can go into which kind of requests or responses. So we have the top, the response entity. Then we have all kinds of entities that can go into a request, and these are a subset of all the ones that can go into a response, so these extend from response entity. Then we have message entity, which is just request entity, which means these are entities you can use both in a request and a response. Okay, then another one is body part entity, which body parts are parts of multi-part form data messages. So if you have HTML forms which upload files, for example, you will have to do with body part entities. And then we have some kinds of entities which you can use in any context, and these are the universal entities. So these are now just the marker traits, and now come the concrete kinds of entities. So, basically we say the body of an HTTP message always contains of a content type, and then the body can be either strict, which means we have all the data currently already available. So if you produce just a simple output string for a response, it will probably be a strict entity because you have all the data already available. So this is the usual case and can be used in all kinds of contexts. Then we have default, which is the default streaming case. So what we have in here, instead of a strict byte string, we have a stream of byte strings. So you must say how long, how many bytes you will produce from this data source, but you don't have to provide all the data up front. Okay, then we have the chunk entity type, which is a representation of transfer encoding chunk HTTP messages, which you can use in responses and in requests, but not in body parts. It just doesn't make sense there. Then we have a feature from HTTP 1.0, the closed delimited. So the closed delimited entity is an HTTP message which doesn't specify a content type, content length, but delimits the data by closing the connection in the end. So this is the type of entity you can only use in responses but not in requests, but it wouldn't make sense to use it in requests because you can't close the connection after you have sent the request. And then we have a similar thing. It's basically the same as closed delimited for body parts. It's called indefinite length. Okay, then we have the model for lots of HTTP headers. Here's just some examples. for example, the set cookie header takes or delivers the cookie, and the cookie itself is a model which we built, which contains the usual cookie fields like for set cookie, it's probably the key, the value, what's it called, the content, the path, the domain, and stuff like that. Then we have the escape hatch, is the raw header. You can use the raw header if we don't have modeled your header, or if we receive a header which was modeled, you will receive a raw header, which is just, as you know from other frameworks, just the key value pair. So how does our stack look like? So at the bottom we have the operating system. So this is clear. Then we build on the asynchronous Java Neo API from Java, and on top of this we some time ago we introduced the Akka-IO part of Akka, which already is an Akka actor available since like 2 years, and it's an actor-based abstraction to do network I/O in an asynchronous fashion. So we still build on top of that, and now with the new reactive streams, we already have some kind. We extended Akka-IO to support streams instead of the actor-based model, the old one. So, on top of this, we now have a new model, Akka-http core. In Spring, we had a huge forest of different modules for all kinds of stuff, and now we unified lots of those models to make the whole thing a bit easier to understand. In Akka-http core, we have the model, and we have all the low-level stuff like the real implementation, the parser for all the headers and the model and actual requests, messages and rendering and stuff like that. And then, on top of that, we have Akka-http, which you don't have seen yet, which provides high-level abstractions over all of this, because most of the cases you don't really have to deal with all the low-level stuff from HTTP, but you want some better APIs to work with it. Okay, I think I've said most of this. Yeah, so we have Akka-IO. Yeah, we also have Akka actor and a stream-based version implementation of SSL based on Java SSL. Yeah, that. Right. So yeah, HTTP core is the low-level translation part, which really does the translation between TCP or byte level encoding to our model. Actually, that's not quite correct anymore, because there's clearly separated layer of actors provided as an Akka extension. This isn't really correct anymore, because now we are based on streams, so we don't have any actors of our own anymore.
Just one.
Just one, yeah, currently. So yeah, then we have the high-level part, which really currently it just consists of the server part, but will have a rich client-side API to make it really easy to work with HTTP. So one thing to do is we want to support marshalling and unmarshalling, which means if you have your domain objects and you usually want to send them over HTTP, they have to be encoded in some form. So one common way to do this is to convert them into JSON. And this is well,
Much better.
It's okay. Okay. Another thing Akka-http provides is decompression and compression support for gzip and deflate the common things in HTTP. And a big part of it is the routing DSL, which allows to really, in a very high level, to declare how your request should be handled. Okay, the routing DSL is an internal DSL, so you write your whole routing structure and routing logic in Scala code. Or we use Scala because it's so type-safe, and we can really express we can express things in a high-level way, but it's still very type-safe. We don't just say which requests go into which path or into which handling, but we can also define more of the behavior of the handling of the request. And all this is done by combining simple directives, how we call them, which are just small building blocks for one specific kind of thing. And you will see how this works together. So, okay. For Spray and for Akka-http, we don't want to provide a complete framework where you have to build your application inside the framework. But we won't really mess with your application at all. Instead, you implement your application core just like you've done before. You define your domain object and build a service which you then want to provide the REST API to. And that's where Akka-http comes into play. It sits next to your application, receives HTTP requests, converts them into your domain objects, and lets your application handle the request, gets back another domain object from your application, and then really translates it back into an HTTP response. So, yeah, as I said, the point is that you completely separate the point where you make the translation between the HTTP stuff and your domain objects. So yeah, the API layer, so the routing DSL allows to match based on different things in your HTTP request. The common ones are obviously paths and HTTP methods, but you can query all things which are really in the request. As I've said before, yeah, we do the conversion between domain objects and HTTP things. We do encoding, decoding. We have directives for authentication, authorization. Yeah, we have we support the basic things you need to do to serve things on the web, like server-static content as well. And we try to be RESTful with the error handling, so we have also a rich model of errors that can occur. So like one error is like 404 when a path wasn't matched, or another error is when you can't read a message body for some reason, because either you don't understand the media type. This will result in one status code, and other errors will result in other ones. We have this all modeled. So this is basically the same, it's another example than before, but you still see we have the IO HTTP bind. It's basically the same code as before, and run with by coding, so this is the same. But now to provide the implementation of your handler, you can use our routing DSL. And you wrap it with run route, and inside you have kind of a tree of directives which specify how requests should be handled. So let's see this. So here we have the first block which says path. So we match all requests which start with order, and then in the second segment of the URI have a hex int number, which is just the formatted string in some way. If you use things like hex int number, it will read the hex representation of the number and convert it into a real integer object and provide it to the inner block as ID, as you can see. And this ID will already be typed as an integer. So if you would, if someone would request with the URI where this second segment wouldn't be a hex number, wouldn't be a number, and couldn't be passed, you would instantly get an error. So inside we decide if it's a get request or a put request, and so on the leaf level we say what the action is which really should done. And in this case we just output a string and return it as text plain to the requester. So these are all the directives we had in Spray. In Akka-http we will mostly have the same set. I think Arthur will tomorrow show you all of them, right? No, but he will show some of them in his talk and explain how you build routing, you build the service with the routing itself.
Yes, so there's one more thing that we want to show you, which is a real-world example of what a service might look like if you define it in the Akka-http high-level server-side API. So let me scroll to the top. So basically, this is from Spray, but it doesn't matter. It will look more or less the same in Akka-http. As you can see, this nesting that Johannes has just shown can go on for quite some levels and can go quite deep. But it should result in something that is quite readable and maintainable, even for you when you come back to your code in a year or something, right? We all know you sit down, you think up something nice, and then it runs and you let it sit there, and half a year later you need to extend it or fix something. And you go back and you were like, oh, how exactly did that work? I'm not quite sure, right? And the goal is, with the high-level DSL, that ties together different parts of your application on the API surface, that you can still go in and understand exactly what's happening. And so let's just quickly take a look at what this route defines. Akka will show you all about the details of what exactly, how exactly this works and how you combine it. So the goal is not to understand it completely, it's just to get a feel for what it is. So on the very outside, here we just say encode response gzip. This thing does two things, right? You just wrap everything else with this, which results in all responses that are being produced by the inside to be gzip compressed. That's it. You just wrap it with gzip compression. That's the one thing it does, but it also does something else. If the client comes in and the client does not accept gzip compression, then the client will get a proper error, right? And it will make sure the client actually sees the reason why the request wasn't accepted. Because there's no point in your business API that you might sell off to some customers if they try to use your API, but they make mistakes, of course. But if they don't know what is wrong, what went wrong, what mistake they made, then they'll be frustrated and they won't be paying you big bucks for your nice API, right? So we need to make sure that all the responses that the clients get, if they make mistakes, contain as much information as possible for them to actually figure out what the problem is. And the encode response on the very outside will tell you exactly if you don't accept gzip compression, 406, I think, or maybe not, some proper status code that is defined, and tell you, well, we cannot serve your request because you don't accept gzip compression. Very simple. And you don't have to worry about that on your server-side stuff. You don't need to think through that. You just wrap it with encode response, and encode response does it, which is nice. You can leave it away, and then it won't be compressed. So here we just match the root resource, and we just redirect to /doc, whatever the documentation is. And then all the requests that start with API, they go in here, and then we have something else. That's if it's /API/top articles, whatever that means for this business service, and it's a GET request, then we expect a certain parameter called max, which must be there, and it must be an integer, right? And only if both of that actually hits, then we get in here. If the parameter is not there, the client will get a proper error message telling it that max needs to be there as a query parameter. If it's not an integer, the client will get a proper error telling it your max was there, but it's not an integer, right? It's all implicitly done write. And then we validate this. This is one way of validation, where we say, okay, it can only be greater or equal to 0, right? And you can probably think what the error is going to look like. So what happens here, what we do is we complete the request with this thing. And you probably know Akka, you know what this results in. This is, in the end, an expression that gives you a future. A future to the response that the top article service actor will send after you've sent it a command, right? In this case, the command is just an integer, which is not very properly typed, so yeah, but still, that's how this works. And we expect the reply that comes back to be a sequence of article, whatever article is, right? As you've seen before, as Johannes has said, the important point is, from our backend, we expect domain objects, right? The backend doesn't know anything about HTTP, so there's an article, maybe this is a book, right? Now we use this, so we complete the request with a sequence of books. So with a future of sequence of books. So the marshalling infrastructure that comes with Spray already knows how to unpack a future, so you don't need to worry about the future. And we also know how to do sequences. In this case, it's a JSON response. So sequences, we know, okay, we can produce a sequence of a JSON from sequences, but you need to somehow supply the information. How do I translate an article into JSON? That's the only thing that you need to provide, right? If you say, okay, an article needs to be converted in the following way into JSON, then this layer will do everything else. It will unpack the future, unpack the sequence, and just properly render it into JSON. And the way you do this is probably something that Akka will talk about tomorrow as well. So let's go further down. Then there's another thing. For example, this is something that is not delivered by Spray. This is a custom directive that is easy to write. So whoever wrote this service had some way of authenticating users with some kind of token, probably looking at a header or something, or at a cookie. And it's easy to write code, like your own custom logic, and package it up in a directive. Because this way, you know, okay, cool, maybe there's a whole logic, a lot of logic running behind this. But here, it's just one line that is easy for you to digest and understand, right? So we want to make it easy for you to separate out your logic in your API into small, easy to understand pieces that can be individually tested, individually assembled, and so on, right? So that you can use it in this composing fashion. So this token authentication maybe is asynchronous, talks to the database, does whatever, and gives you in the end a user object, which is a properly typed object in your case. And then if we could authenticate, and the path is /ranking and a GET request, then there's another custom directive called count time that probably just counts the number of requests it goes through there and measures the time that the service needs to compute the response for this, which is easy. And then there's a whole bunch of parameters that are optional in this case. As you can see with the question mark 0, so if they're not there, they have a default value. And they all can be specified by the client, and then they're packaged up as a case class instance. Because we don't want to deal with them individually, right? We could just deal with them individually, but then we'd have 5 parameters all the time, and it would just clutter up our API definition. So it's much easier to just immediately package it up into a case class, and this is what it does. So this gives you an instance of the descriptor, whatever this is. And then the same pattern, we send it off, this is a command, we send it to the ranking service, expect a ranking result, somehow implicitly provide a format for how a ranking result is being converted to JSON, and this goes out across the wire. So there's complicated stuff happening in these few lines here, but it's nicely separated out, right? So easy for you to read, easy to maintain, easy to change and understand, and you get back to this. And then there's more. We don't really need to go through everything. Here's a post request, so this is only authorized if the user that we've extracted is an admin, right? So there's some is-admin that the application provides, and then this will only work. This is something, the authorized directive is something provided by Spray or Akka-http. This is all custom code. And if the user is not authorized, then it will obviously get a proper error message telling you you're not authorized to post to accounts. And This extracts the content of the request in the same way, just the opposite direction of marshalling. Like this unmarshals what the user has sent in the request into a domain object of type count details. And this needs to be successful, and it needs to be there, and only if this works will you actually get, then you will get the details here. And then the same thing and the same thing. It's good, don't worry about it. It's fine. Yeah, sure. Good. There's one interesting thing here, which is exactly what we've seen before, because these guys actually had this. They had a version 1 still running in their Django or wherever, right? And for certain requests that go to /v1, we would just proxy it over. And the nice thing is, because Akka-http gives you client-side as well as server-side APIs, and we have the same model, right? The header is the same for the request and response. It's very easy to actually translate one request into another request, just change it, and then proxy the response as well, because it's the same model. If you use traditional other frameworks for working with HTTP that only give you one side, for example, the Ning async HTTP client, right? It's a great Java library, but it's client-side only. It has its own request model and so on. So if you needed to translate the incoming request into a request that you can then send out with that client framework, you'd have to do a lot of work. And probably things wouldn't quite fit together and it would be painful. Once you have something like Akka-http, proxying is very simple, because it's the same thing on both sides. And then there's more that we can skip. Down here we have some resources, so we can say you can serve static content either from the file system or from the class path, which is a nice pattern for things like documentation that you could just wrap up into your jar and just serve it from the class path if you need to. Of course, you can just also forward to another server that you have and so on. So it's completely flexible. Good. We're almost done. Best practices. As I said, it's helpful if the route structure is clean, readable, there's not too much code in there. If you find yourself having to put in a lot of logic, then it makes sense to kind of pull it out into your own directives. And it also makes sense to keep the architectural separation between the API layer that we've seen and the core of the application in the back end, which is helped by the unmarshalling and marshalling infrastructure as we've seen. Error handling is important, especially if you have someone paying for your API. And then just as a practical tip, there's an SPT plugin called SPT Revolver, which is great for really fast turnaround of working with things like Spray or Akka-http, because it will just give you an immediate restart of your application as you develop. So there's more that we could talk about. There's infrastructure for testing routes, because of course, if you have complicated logic there, you want to make sure it runs properly. There's a test kit that we provide. There are client-side APIs, which are a bit less prioritized in the beginning now, but nevertheless we'll have good ones. And there's JSON support. There, of course, you can easily tie in your favorite JSON solution. There are all kinds of JSON libraries nowadays, and you might want to use whatever your favorite is. It's easy to just plug it in and have a proper adapter for that. Let's spend a little bit. It says Akka-http roadmap up there. Everything else is on the chart. So we're currently in the process of, we're actually quite far. That's the good thing. The agree and specify reactive streams API is something that is not on our plate. It's something that Twitter and Netflix and TypeScript and Red Hat are doing right now, and they're very close to actually signing off on version 1.0 of that, which is important because it's one of our main dependencies. But there are already milestone releases available that we're currently building with. And then the goal is, of course, to finish the first proper release of these new modules that Johannes has shown, the Akka-http core and the Akka-http modules. Because we're depending on the reactive streams implementation on Akka Streams, this goes hand in hand. And we're very close there, as you can see. The low-level layers are almost completely done. There are a few things missing on the client side, but apart from that, this all is running already. You can actually use it. It has been a bit unstable in terms of its API naming and structure in those last weeks, because we've been learning a lot about how to provide a proper stream-based API, and there's a lot of new work that we've done there, because this newest version, even though it seems simple on the surface, it actually has more to it than you initially think it is. So in the last year, we've wrestled with proper streams, ESLs and APIs to make it as easy and natural for you to work with streams. And on the high-level side, we've been making good progress on the server side, pretty close to completion there. And on the client side, it's, yeah, as I said, we're a bit behind. But nevertheless, we want to make the server side available as quickly as possible so that you can use it. And we can get your experiences in, because we very much depend on your experience as you move on to this, what you like about it and what you don't like about it. There's one thing, the most requested ticket in Spray is this add WebSocket support. When do you add WebSockets? We need WebSockets. There's a ticket on GitHub. You can sign off with +1, like the 157 people that have already done it. We will put it in, mainly, and not only, but especially because Play wants to move onto this new stack, and Play relies and needs WebSockets. So Play cannot do it if you don't have WebSockets, so we need to do it finally. The reason we've been, why we've been kind of pushing off a little bit on this is because we knew that we will have to rewrite the whole bottom layer of the stack anyway, by moving on to streams. And then if we already had a WebSocket implementation, it would have been a lot of work to just completely redo that. So that's why we kind of like, oh, let's do it once we're on streams. And now we're on streams, and as soon as the other things are done, we're going to just bang it out, and you can use WebSockets in a streamified fashion for gigabytes of XML data or anything. And then, in the end, of course, the goal for TypeSafe is, and it makes sense, to move Play onto this new shiny stack. Right? That's the end goal. Currently, Play sits on Netty. Right? You don't see Netty really, because it's a driver layer underneath. But even though Netty is great, and those guys definitely know what they are doing, it's still not the native stack for TypeSafe, right? It has all kinds of, as I said in the beginning, a bit of friction here and there. And since we have this new fully asynchronous and nice, natural HTTP stack there, Play will want to move on it, and it will do so in an incremental fashion. So at first we'll add a new driver, so to speak, to Play that you can just switch on, and nothing will change on top. Just continue to work as it does right now. That's the plan. And then once we've got, gotten some experience there, then the old one can be deprecated at some point and so on. So there will be some time where you could choose between the Netty-based implementation and the new one. And eventually, if you know Play, you will know that they have a different HTTP model. For example, the header in Play is just a string tuple, right? It's not properly typed. And of course, since we have this nice model, we actually want to make it available to you as a Play user as well, which will take some more time because it would mean changing the API. So we want to see that in the, I guess, in the 2x session release train of Play. Yeah, so much for the roadmap. Thank you very much. Questions? Yes, Tim.
Were there any dates attached to that roadmap? Has there been
any dates? Yes. That's a classic question that we always dodge. Yeah, of course, everyone's asking for dates. We can definitely say that we will be done with porting everything from Spray into Akka-http that we want to port very soon. So originally we had the end of October, which would be next week. It's probably not going to be possible to have everything ported and regularly reviewed and merged until then, but it's only a very short amount of time out. So in November, we hope to be completely done with porting Spray. The parts of Spray that we want to port, there are a few parts that we don't want to port, like the Surflet module. But starting in November, you should see a release of Akka-http that has all the features, that is completely running, and you can move on it. There will be some drawbacks. For example, performance will be significantly lower right now. So I'm just saying that right now because you might be surprised that it's quite a considerably bit slower than Spray it is right now. But it's not an intrinsic problem, it's just that we have not spent any time on optimization so far. So just because we want to make sure we get it correct first, and once we know we have the right structures in place, there are tons of options that we have for making it run faster. But we have intentionally held back so far on going there, right? Because we all want to optimize, and we're like, oh yeah, let's optimize. No, not now. Let's do it later, right? So it will be slow in the beginning, but it will very quickly become faster. Other questions? Stefan?
Do you have control over the pipeline? I mean, the way that the packets are transformed. Can you edit it and edit it at runtime?
The whole stack, as you've seen, is all part of Akka. So it's Akka that sits on the Java NIO part, which means that we have full control of the full stack. We want to make it, as you might have seen in certain aspects, we want to give you as much control as we can for maybe injecting your logic in between those layers. So if you want to do something in between Akka-IO and Akka-http core, then you can do that.
For example, can I plug and unplug SSL on the pipeline?
Yes. Yes. Because that's, for the HTTP part, that's transparent for us. But that's the transport that I showed in the beginning. Let's see whether I find it. There's this thing here, on the client side, for example, where we say the very last one, right? You give us the transport, which is a piece of pipeline, right? And we just decorate it. And whatever you put in there, that's yours to choose, right? And normally you would ask the I/O layer to give you this pipeline, and you just plug it in there, and then you'll have the HTTP level thing. But you can inject stuff, you can have your own transport, and so on. So that's the amount of flexibility that we can give you, right?
One last question. Here we can see that you use byte strings. Do you think you will provide something like memory pooling, like it's being done in 84?
Memory what? Pooling?
Pooling.
Currently not. Currently we think the byte strings are all you need. For giving you an immutable blob of bytes as a chunk of a larger string, they are a natural choice for us. There might be other optimizations. The memory pooling that you're talking about, I haven't really looked into much. But currently, this is good enough for us. Yeah. Other questions? George?
I might have missed this, but are you planning to also migrate type-safe routing, and if so, will Akka depend on shapeless now?
No, good question. Spray uses for its routing DSL shapeless you don't really need to work with it if you don't care, but there's shapeless as an integral part of the API, and we've been spending some time in thinking about how we might include shapeless and so on, because it's a great piece of technology, but it would complicate our build stack right now, because once we are in Akka, we are really close to the standard release train, and if we have a new Scala version, then we need to build Akka for that before shapeless is available, and this is kind of like a circuit dependency, and it's difficult to work with. So ideally, we want to manage dependencies very tightly. And with the help of Miles, actually, we found a very nice solution. We just moved off H-lists into tuples, and we just have tuples now, and it works almost the same way, so the DSL looks exactly identically as it does, and we don't need shapeless. You can still, of course, use shapeless and so on, but there's no hard dependency on it anymore, so we dodge that question. Yes. One more question, last question. That's it. Great. Thank you.